We will now see how we can find responses in time of fractional order systems, and for that we need something similar to the well-known inverse Laplace transform of a pole, which, as you know, is an exponential. Let me call your attention to the fact that if a is positive, we will have a negative exponential that, as time increases, converges to 0. If a is negative, this minus sign will cancel the minus sign of a. We will have a positive exponential that diverges to infinity as t increases. We can make this explicit by adding a minus sign here and a plus sign here. The exponential, as you also know, can be found from its Maclaurin series, which has here in the denominator a factorial, which can be replaced by the gamma function minding that shift of 1. It turns out that to find a result parallel to this for fractional order poles, we need an extension of the exponential. A well-known extension of the exponential keeps the numerator in these fractions of the series, but in the denominator adds a parameter here to function gamma. This function is called the Mittag Leffler function. I have just wrote the definition of the one-parameter Mittag Leffler function, so called because a further extension is possible by adding a second parameter to the denominator, here replacing this 1, which appeared because of the shift of 1 in the gamma function when compared to the factorial. This is the two-parameter Mittag Leffler function, and this is the function we need to find a result similar to this for fractional order poles. Let me right away call your attention to a result which will be important in what follows. We know that e power 0 is equal to 1. If I try to find this from this series, I can do so by separating this series into 2. I will keep in the summation all terms from 1 on. In the numerator, I will have 0 power k. K is a natural number, so 0 power k is 0. In the denominator, k factorial is an integer number, and consequently, this entire summation is a summation of zeros. All this is 0. Then I still have the term corresponding to k equal to 0. In the denominator, I will have 0 factorial, which, as you know, is equal to 1. In the numerator, however, I will have 0 power 0, which does not exist. We might thus conclude that we cannot use this series to find the value of e power 0, but in fact we can if we use a trick. I will replace 0 power 0 by t power 0 and take the limit as t goes to 0. This t is consequently different from 0. T power 0 is always 1. So here I have a limit of fractions. They're always 1, and of course this limit is 1. A similar thing happens with the Mittag Leffler function. Let us consider right away the case of the two-parameter Mittag Leffler function, since this is the version of the Mittag Leffler function that we will need. we will find the value of this function for 0. Again, I can separate this summation into 2. Here I will keep all the terms from 1 on. In the numerator, I will have 0 power k, which, as we know, is equal to 0. In the denominator, I have some real number given by the gamma function, and consequently, I have a summation of zeros. All this is 0. As to the term for k equals 0, the same happens. I will have here gamma of alpha multiplied by 0 plus beta. In the numerator, I should have 0 power 0, but since this does not exist, I will use the same trick. Put here t power 0, take the limit as t goes to 0, and now I have a numerator which is 1, and a denominator which is constant. Since what is inside the limit is constant, the limit is equal to 1 over gamma of beta.